Alright, so our goal here is to actually write a whole bunch of recurrences as sums in general, but we don't really know how, so we're going to come up with some theory. Now, right now, the best theory we have is, I don't know, we're going to multiply by something, okay? And this something is going to be Sn. So we're just going to multiply both sides by some completely unknown term, Sn. You're like, this is really stupid. And I'm like, I know, but it's going to work. And that's why math is amazing. So we've got Snbn, T sub n minus 1, and Sncn. Alright, got it. Now, what we super duper wish, I wish I was a fish. I want to wish that it looked like this. So I wish that it looked like Sn is equal to this thing, Sn minus 1 plus stuff. Alright, so that's what I wish. I wish that somehow I could rewrite this and this as being related by like some kind of n minus 1 term. It's basically the same thing except it's an n minus 1 term. So basically by that what I mean is we wish that Snan was equal to, or sorry, Sn minus 1, An minus 1, that's what I meant to say. I wish the left term reduced by exactly 1 would be equal to this term, alright? But it's not. But if it was, that would be awesome. I mean, I guess it could be, and that's the point of what we're doing. So really what I wish is I want to come up with an Sn term such that Sn, let's see, A sub n minus 1, B sub n times Sn minus 1. Alright, but I don't just want it to work for n and n minus 1, I want it to work for n minus 1 and n minus 2, which means that this is going to go look like this. And then if I throw in an n minus 2, it's going to look like that. Alright, and then I don't want it just to be for n minus 1 and n minus 2, but also n minus 2 and n minus 3. So you're getting where we're going here? You smell where I'm stepping. Alright, an minus 3. And basically this is just going to go on and on and on to here. And b sub n minus 1, b sub n minus 2, and over down to bn. And s not, right? Because this one and this one match. So those two and those two match, and that's one more than that. Alright, now it looks like we're stuck, but we're actually not. But wait, there's more. If we were to actually take this right here and plug it in for Sn, oops, that's not helpful, Sn, and Sn, all the S naughts are going to cancel out. You're like, well, yeah, because everything's going to cancel out. I know. But the S naughts can all divide out as long as they're non-zero. So at this point, we get to make a decision. We're going to let S naught equal 1. So basically what we're now going to do is you can't tell, but we're done. This is the dumbest thing I've ever heard. But we're done. Because basically what we've done is we've set up a system. We've come up with an S sub n such that once we get the S sub n right, then we can rewrite this summation that we have here as, or this recursion that we have here as a summation. So again, this is one of those things that's not going to feel like you did anything at all, ever. So like a minute ago when we had the Towers of Hanoi problem, we basically went through here and we said, okay, so we had t sub n is equal to 2 t sub n minus 1 plus 1, right? So our little s sub n, remember an is the coefficient on the first term here. This is our an right here. Now those are all just 1, so we had 1 times 1 times 1 times 1, all the way down to 1. And on the bottom we had 2 times 2 times 2 times 2, all the way to 2. And on the bottom there were actually n of these, which means that we had 1 over 2 to the n, which is why we ended up dividing everything by 2 to the n, is we were able to do this and come up with this. So this is actually going to work. I'm going to do another video where I do a whole other problem, but basically here's the theory that you're going to want to go through. Okay, so basically you're going to be given this kind of a weird recursion, and these don't even have to be linear. These can be factorials, these can be powers of 2, or 2 to the n, or n squared, or I don't know, sine and cosines. I don't know. It should all work out in theory in the end, if you can get it to work. Alright, you're going to choose some kind of S sub n based on the ratios of all of the, or most of the A sub n terms over the B sub n terms. Now, if for some reason this A sub naught or B sub 1 turns out to be 0, you can stop at A1, B2. That's okay. And in fact, yeah, anyway, so you're going to multiply your original equation by whatever Sn is and simplify. Then you can recognize that pattern. So, I mean, when it comes down to it, you're going to set big S sub n is equal to little s sub n, a sub n times t sub n, but don't memorize a formula as much as you're trying to figure out what's going on. You're trying to find that pattern. Then you're going to write it as a sum, try and simplify if you can, and then go ahead and reapply that t sub n from what you had up here. So basically you're just going to reapply that except in the opposite direction. This is crazy because this stuff actually works. You can apply this to all kinds of crazy things. So I'm going to put together another video and show you guys that.